Bismillahirrahmanirrahim. Assalamu alaikum, dear students. This is our next problem. Problem having been taken or chosen or selected from the book Quantum Physics by Stephen Gasiorowicz. As usual, we first come to its statement. Okay. The maximum energy of photoelectrons from aluminum is 2.3 electron volt for radiation of 200 nanometer. Nano standing for 10 to power minus 9. Okay, 200 nanometer and 0.90 electron volt for radiation of 258 nanometer. Okay, maximum energy is also two times given, that is 2.3 and 0.9, and wavelength is also given two times, 200 nanometer and 258 nanometer. Using these data, use these data to calculate Planck's constant and the work function of aluminum. Okay, dear students, actually both these physical constants are given in tables of physical constants. Okay, we will also show those tables. Okay, its answer is known from constants, from tables of physical constants, but we have to check that value, we have to counter check that value, we have to verify that that value is correct. So in this case we do not claim to reach the exact that value. Our value should be close, very close to that value. Okay, if our value is close to that value, then we will say that we have succeeded in solving the problem. Okay, Planck's constant H value, Planck's constant is given in table of physical constants, and usually it is given in two different set of units. Okay, moreover, many tables are given in usually books of solid state physics, in which work functions of various elements are given. Okay, so dear students, now we are going to its solution, but before going into the solution in a formal manner, we will have to go through a few snapshots. Okay, dear students, here Planck's constant H, this value is given in two different system of units. Okay, in joule second and also in electron volt second. However, work function aluminum is not given here, that will be given in some other table. Okay, now we move to other snapshot. Okay, next snapshot, dear students, this snapshot is about photoelectric effect. We have dealt with this snapshot in our previous video, so we will not give more time to this snapshot. Okay, next to this, some basic knowledge, some basic information about work function is also given as a reproduction. Okay, this entire text has been taken from Wikipedia. Okay, so if we want to know some information about work function, then we must concentrate on this text. Okay, we do not give more time to this snapshot. Okay, we move forward. Next, there is a table of work functions. Okay, some photoelectric work functions. Okay, here dear students, aluminium comes at a second number. Okay, aluminum 4.08 electron volt. Okay, aluminium work function is given as 4.08 electron volt. Okay, we have to, our answer should be close to this, okay. Even if our answer becomes 4.2, it will be very close to 4.08. If it comes 3.9, even then it will be considered that we have reached correct value, okay. Dear students, now we are starting our problem in a formal manner, okay. We know that h nu is equal to hc over lambda, and this alternatively becomes equal to w plus k. Rearranging above equation, we get this implies that k becomes equal to hc over lambda minus w, equation number 1, where h nu is the photon energy, in which h is the Planck's constant and nu equal to c over lambda is the frequency of photon. W is the work function of the metal, and k is the kinetic energy of the electron leaving the metal. Okay, so this thing gives us a solid foundation regarding the solution of this problem, okay. Now equation number 1 gives, okay, equation number 1 implies we are reshaping equation number 1 in two different further equations, because we have been provided with two sets of values, okay. One set one wavelength and energy, and second other wavelength and energy, okay. So we are reshaping equation number 1 in two further categories, okay. Here k1 equal to hc over lambda 1 minus w. Here we have not used w1 and then w2 in equation number 3, because work function is the same in all cases, okay. Here two sets have been provided, but it does not mean that work function will also have two values. Work function will have only one value, which is also provided in the tables, okay. Similarly, k2 equal to hc over lambda 2 minus w, okay. So we have done nothing. We have just reshaped equation number 1 in two further shapes according to the nature of the problem, okay. Now equation number 2 implies that what we are going to do, we are just putting the values, okay. In place of k1 we have used 2.3 electron volt, which value has been provided in the statement. In place of hc we have used its alternate value 1240 electron volt into nanometer, okay. This value has been taken from the table of physical constants, which was shown as a first snapshot, in which value of Planck's constant h is given separately and value of speed of light c is also given separately, and in addition to these separate values, their combined value hc is also given, okay. So here we have taken that combined value from that table, okay. Moreover, value of lambda 1 is also provided in the statement, 200 nanometer, okay. Here we will not have to convert nano into 10 raised to the power minus 9, because nanometer will be cancelled with nanometer, okay. So dear students, this implies that 2.3 electron volt is equal to 6.2 electron volt minus W work function. Now we have shifted work function W on other side of equality and it has become positive, while we have shifted 2.3 on other side of equality and it has become minus, okay. So work function has become equal to 6.3 electron volt minus 2.3 electron volt, and this finally becomes equal to 3.9 electron volt, okay. So dear students, in table value was given as 4.0, okay. 4.0 and 3.9 are very close to each other, so we may say that we have solved problem almost to satisfactory extent, right, okay. Now equation number 3 implies, now the equation number 3 gives what we have done, we have just put other set of values in equation number 3, okay. We were provided with two sets of values, one we have put in equation number 2 and one in equation number 3, okay. When we repeat the same process as for equation number 2, we finally reach the value 3.9. Okay, so it means this is this is actually counter check that our result has become same according to both values. Okay, as per equation number 2, work function had become 3.9 electron volt, and as per equation number 3, it has once again become 3.9 electron volt, and it is very close to the value given in table, that is 4.0. So we assume that our approach is correct, right? Now dear students, we are subtracting those two equations, that is equation number 2 minus equation number 1. Okay, equation number 2 minus equation number 3 implies or gives that or becomes k1 minus k2 equal to hc over lambda 1 minus hc over lambda 2. Okay dear students, here w does not appear because w will be cancelled with w when we are subtracting. Okay, because work function is not taken as w1 w2 because it is same everywhere. So work function is cancelled and we are just left with these values. Here we have k1 minus k2 becomes equal to, here we have taken hc as common, and then LCM of these two becomes lambda 1 lambda 2, and in the numerator lambda 2 minus lambda 1. This implies that from here we can keep h Planck's constant on one side and shift all other values on other side of equality. So lambda 1 lambda 2 which is in the denominator will become in the numerator on other side of equality. Similarly, lambda 2 minus lambda 1 which is presently as appearing in numerator will become in the denominator. Moreover, speed of light c is being multiplied with Planck's constant h, but it will be divided or when shifted to other side of equality. Okay, so this implies that h becomes equal to this, and now we are putting all these values in it, and hence we see we do not explain it more. Okay, these are just simplification steps, and if we explain these simplification steps, I think it will be equivalent to wastage of time. Okay, because this mathematics is of almost middle class level or secondary school level. So its value becomes a value of Planck's constant h becomes equal to 4.1545 into 10 raised to the power minus 15 electron volt into second. Okay dear students, when we compare this value with the value of Planck's constant given in table of physical constants, which was included in as a snapshot, first snapshot, we see that this value is very close to that value. Okay, as I had said in the beginning of this video that we do not claim to reach the exact value, we will reach closest value. Okay, so I think this value of Planck's constant is very close to the value given in the table, and hence this is the end of our video. This is the end of our problem. Till next video, Allah Hafiz.